Good. So we are recording it as well. And has somebody got connected to the meeting? Huh? You were connected? Acha, that was speaker. Okay. Good. So you all can see who are sitting here can see the screen. You can hear me and look at the screen. So first, what we'll do is we will continue with what we were discussing earlier. Let me download some files. So there will be a slight lag, but you'll have to bear with me here because we are short of connectors. So I told you that I will discuss the bubble column case with you. So for the bubble column case, we need a geometry and we need one FLML file. So these two files we will have to copy. And then we'll have to start the virtual machine. So we'll have to share the files from the desktop to this virtual machine. So for that, I'll have to go to settings and share some folders. So let's say I share this folder and I'll make it read only just to be safe so that from inside the virtual machine, we can't create any problems. There's some problem. Let's try again. This doesn't work. Let's try the other way around. It's able to read my USB now, so I'll read from there directly. We go to desktop. So we are in the folder. We have a geometry file now. So I should be able to, let's increase the size of the screen. You can read this. So let's open this geometry file. So this is how the geometry looks. It's very straightforward. You have a bubble column. So it's a two-dimensional geometry. So at the bottom, we have an inlet, and then we have boundaries here. So you can actually, if you try to look closely, you can see there's a point here. It's not very nicely visible on the screen, on the projector, but on my screen it's visible quite nicely. So we have points here. So we have this point. If I go take my mouse there, it says point number 1, position 0, 0, 0 on boundary of curves 1, 6, and there's a mesh attribute size. Then I have another point, which is point number 6. Its position is in the x direction, it's 0.09. It's on boundary of curves 5 and 6, and mesh attribute size is there. For every point, we have something like that. And if I take my mouse over a line, it says line number 6. Boundary points are 6, 1. So you can see that point number 1 and point number 6 are the boundary point for line number 6. And if I take my point here, then it's on boundary of curves 1, 6. So this is line number 6, and this should be line number 1. Okay. So the geometry has been created bottom to top. So what we have done is we have created points, joined points to make line, and connected lines to make a surface. That's the for simple geometry that works quite well. For complicated geometries, you may have to work other way around. So you'll have to start with an object and then remove something out of it and so on. But bottom top, if you can do, that is most intuitive because you understand the geometry very well. Okay, so we have lots of points. There's another point number 5 and so on. And in case I want to add a point, I can always go to geometry, elemental entities, and then I can add a point, and I can create a point somewhere. The grid right now, I can change the grid, I can change snapping settings, so I can create points. But I think you understand what's happening here. Now let's say I want to understand this text-wise. I don't really want to go to the GUI. I want to create things using text. So see, I know how many points I need. So I say, I write this complete thing is what you saw on the screen. Okay, these are the commands for creating that geometry. So we have points, point 1, point 2. So these are numbers for points. These are coordinates of points. And every point has a corresponding mesh size associated with it. Okay, so an LC is simply a variable that is equal to 0.005. So we have 6 points in total. Then I say that my line number 1 connects points 1 and 2. Line number 2 connects points 2 and 3 and so on. So I have 6 lines. And then I say that I want to create a line loop. So lines 1, 2, 3, 4, 5, 6 in this order. There's a loop called line loop, and that loop number is 5. And from that loop of lines, I make a surface whose ID is 6, and that has been created using loop of lines called 5. Is that clear? Any questions? Loop is, you can say that. Yes. Yeah. But the order is important, okay? Otherwise it gets confused. Then, so this surface is my surface where all the fluid mechanics will happen. Next is I need boundaries, because I will want to specify boundary conditions. So and for this we need physical lines. Okay, so we need a physical line. The ID is 331. This is some ID I've given, and that is equal to 6. So line number 6 becomes physical line 331. So lines, you can have many of those, but physical lines are the lines which can then be read in terms of when specifying the boundary conditions. So then I have physical line 332, that is line number 5. Physical line 333, line number 4, and so on. So I've given here that physical line 331 is the bottom of the box. Then you have bottom of the box part 2, bottom of the box part 3, and then we have left wall, right wall, and top wall, or top surface, whatever it is. And then we have a physical surface created, which is number 10, created from a plane surface 6. So this is how things work in Gmesh, and in fact, typically any meshing software will work this way only. So let's go back to this. So this was, now what we can do is, so we have different type. We have physical groups, we have elemental entities, so we can see all those. Okay, so we have elemental entities which are points 1 to 6, and then we have lines, and then we have a surface. Then we have physical groups, which are, we have a physical surface, number 10, that is the whole thing. Then we have boundaries, physical lines, which are 331 all the way to 662. So these are our physical groups. So you can have a look at these things as well. There's no mesh as of now. So we can look at the statistics. If you have lots of points, you can see how many points you have and so on. And then, so while looking at the options in geometry, we can say that what we want to see on the screen. So I want to see only the points. So this shows me points. Then I want to see only the curves. This is curves. I want to see the surfaces only. So this is one surface created from these curves. In this case, it's a 2D thing. There's no volume here. Now I want to see curve labels. So we have these physical curves, so which have labels here. So if I want to specify boundary conditions in fluidity, and I don't remember what is what, so I can open the geometry and see that left boundary is 661 physical curve. So this is the number I will need when specify boundary conditions in fluidity. We can have elemental tags, so that is line numbers. We can have physical tags, which is the physical IDs, which we need actually when specifying boundary conditions. So here you can see that we have the bottom boundary in 3 parts. So if I show you the points, so this is, the inlet happens between points number 6 and point number 5. Okay, so inlet is this one, which is 332, and 331 and 333 are just walls. Is that clear? Any questions? So that's how easy it is to create geometry. Now, for instance, I wanted to modify this geometry. Let me copy this. So I realized that my point so this point number 2 and point number 3 have y coordinate as 0.45. So this is on the top. Okay, so I want to move it further up. So what I'll say is I'll just make it 0.65 each. And then if I open this in Gmesh now, you will see the boundary has changed. So we don't, in GUI, you would have to delete this point and move all that. It's very easy to do it in text format. In fact, you can automate stuff. You can create plenty of geometries automatically and then do CFD on them. That is also possible. We have done that in the past. So I'll suggest you tend to use these tools which allow you to do things based on text. Now, there's another question you may have. What is this 0.005? Well, let me show you. I want to create a mesh now. So let's mesh this surface. We write Gmesh. It's a 2D mesh. And then you write the geometry name. So it runs some commands. And it has created a mesh which has 6227 nodes. And it has 12,000, around 12,500 elements. So now we can, if I do an ls, I can see that I have a test.msh now. So let's open it in Gmesh. So this is how my mesh looks. An unstructured mesh made up of triangles it's in 2D, and this is how the mesh looks. You can see it's very homogeneous, and it is made up of triangles. Now I want to refine the mesh. So all I need to do is, just a second. So if you want to refine this mesh, I can, let's coarsen it. That's much easier to look at. So I can simply make this LC on the top as 0.05. That's a characteristic length. And now we run meshing again on this. And now if we look at the mesh, it is much coarser. So that's how easy it is to refine or coarsen the mesh. There's another thing I might want to do is, I would want to keep the mesh size very fine near the inlet, and you would typically want that. And otherwise you want to keep it coarse. So the inlet is, so this point is 0.11. So that's the left point of the inlet. Sorry, this is the left point of the inlet, and this is the right point of the inlet. So for these, we will have a finer mesh. So I'll say 0.005. Sorry. and the same. Hmm? Oh. Too late. Yeah. Okay. So what we'll so for this right point, we'll also change it to 0.005. Let's save it. We'll close it, and then we mesh it again. Gmesh -2. Let's open this mesh. So now we see that the mesh otherwise is coarse, but near the inlet it becomes fine. That is what we want, because we want the inlet to be fine mesh so that we can specify the boundary condition accurately, because inlet is where all the stuff is entering. So if there's an error associated with that inlet coarse mesh, then you can have very wrong uh, solution coming out of that. Is that clear? So I've talked about the characteristic length. I have talked about points and lines and so on. So I mean, you can actually go to Gmesh website. It's a very powerful tool. I mean, now you can do very interesting things with this. We are using it for a very simple case. You can go to tutorials. So for example, we have t1.geo. So all we need to do is we simply need to copy this. Clipboard is not shared. Right, so I've simply copied it. So let me rename it. So this is the geometry file. So let's see how it looks. This one. Actually, they also have a rectangle, interestingly. Okay, so this is a very basic geometry. There's nothing interesting here. Sorry? Oh, you need more space here. Is that better? I think that's the maximum we can do. So let's look at the text. I'll tell you what it is doing. So it has points, it has lines, it has curves, it has physical planes. It's creating fields. So these fields will then let you specify a mesh which could be changing. So you can have cos and sine values. So you can create very interesting and useful things. If you want to create a surface which is a curved surface, you can create that. Okay. You can also do, I mean, you can have surfaces which have holes in them. So for that, we will require to subtract two surfaces. So you create two and do a minus b. So then that creates internal boundaries. So very interesting stuff can be done using these mathematical operations. And the good thing about these is you can, if later you want to change something out of it, that's easily doable rather than going to the GUI and doing things there. Even there it is possible, but I will recommend you try to use the text prompt because that is more powerful. So enough said about geometry. I'll want to move on from there. Yeah. Yeah.
What we do so that we can do refinement along a line.
So along a line is basically whatever points lie on the line, because lines are created from points. So then for all those points, you change the characteristic length, because characteristic length is associated with points. Okay? Around a point, the mesh gets created. And you can also have regions. So if you want to have a region in your domain where the mesh is fine and there's a sudden change, and then there's a region where the mesh is coarse. So you can define regions, and these regions you can say that in this region the mesh is having some characteristic length, and the other region it is something else. That can also be done. Okay. So let's go back to our mesh that we were interested in. So this was this mesh. So I will create a geometry out of it. So 2D geometry, and I will say that it is um, optimized and it is in binary format. So all the help is available here. So you can see that -2 is for making a 2D mesh. O is optimize is using this optimize flag, and -bin is for binary. So binary is good. So let's do minus. In fact, let's optimize it as well. So optimize will create triangles which look much better. It might spend a longer time to do it, but it will create a better mesh. Let's look at the mesh. Looks pretty nice, this mesh. Okay, so next is FLML file. So we'll have to go back. So let's open this in Diamond. Sometimes what happens is some settings may change. It's a very old version, so it might happen that some settings may not work. So this it will show it in blue color. So blue color means that some things need to be corrected. So let's see where the correction is. So particle diameter has a problem. We'll correct it later. So let's look at this FLML file. So this is your multi-phase bubble column that uses a RANS model and also uses direct quadrature method of moments. Simulation name is bubcol underscore 2D gravity down underscore RANS. That's just a name for it. It's a two-dimensional geometry. The mesh comes from a file which has name bub called 2D underscore buva. And then we have some meshes. We'll not worry about this right now. Input output is a VTK format, and it dumps output file after every 0.1 seconds. It starts from t equal to 0, goes till t equal to 120 second, and the time step is 10 to the power of minus 5. A very small time step. Adaptive time stepping is enabled. We want to make sure the maximum Courant number in the whole domain should be 0.5. So if it tries to exceed that, it will reduce the time step. If the Courant number maximum value is much smaller than this, it will increase the time steps automatically. This is the Courant number field. There is also a check for steady state. So, I mean, we have given t equal to 120 second is the maximum we'll go. But if before that it reaches steady state, it will stop. Physical parameter is just gravity here. So we have two phases, water and air. So water has a density which is 998.2 kg per meter cube. It has K epsilon model enabled. If you want, you can also use some other model here. So K epsilon has two fields for those who understand turbulence modeling. It has a turbulence kinetic energy, that's K, and it has a turbulence dissipation rate of turbulence dissipation, that is epsilon. So both are prognostic, that is we are solving for these using some equation. And these equations have a type called K epsilon equation. We already have given them a type. So as I said, you always start with something that works rather than starting from scratch. Otherwise, there's so many settings, the chances of something going wrong is very high. Then you have a background viscosity, which is equal to 0.001. So that is actually molecular viscosity. So what it does is it has a molecular viscosity and then it superposes an eddy viscosity onto it. So it will add an eddy viscosity onto it, which is calculated using a diagnostic, which is basically a function of k and epsilon, k square by epsilon. Okay. Then eddy viscosity tensor, we also calculate a scalar eddy viscosity out of it. And then we have some length and other parameters, which you don't need to worry about at this stage. So if you understand k epsilon, you'll understand all these things. So the whole idea is that it will calculate an eddy viscosity, which will get added to the molecular viscosity, or what we call the background viscosity. Then we have pressure, which is common for the two phases. So what we do is we solve the pressure here for air phase and then simply copy that onto the water phase. velocity is different for both. So we are solving for the flow equations for both phases. So we have prognostic for both. So this is Eulerian as opposed to VOF. VOF is you solve for only one momentum equation, whereas here you solve separate momentum equations for the two phases. Okay, and then velocity will have its own discretizations and so on. And if you want to check the boundary condition, let's do that. So we have sides. So on the side, the surface ID is 661 and 662. So if you remember, then 661 was the left boundary and 662, I think, was the right boundary. Okay. Then Sparger is the inlet. That was 332. And then 331 and 333 were the boundaries to the left and right of the inlet. So this is where those numbers are useful. We have to specify the boundary. Unlike a software where you have graphical user interface, you click things, here you specify them. And the chances of things going wrong here are much less as compared to where you have made a wrong click and you don't even know what effect that has. And again, these are all text based. You can change them later without going to GUI. So all can happen over the, if you're working with HPC, for example, and when you would want to change something, you don't want to copy the files back and create them on the local machine because HPC will not allow you graphical interface. So this becomes very useful in those situations. Changing those things, textually on, let's say for a case file of ANSYS, is not possible. Or if it all is possible, it's quite complicated. So we have boundaries. So let's look at what boundaries we are applying. So on the sides, we have a Dirichlet boundary with x and y as 0. So that's a no slip. On the outlet, we are specifying only y equal to 0. So we are saying that only y velocity is 0, but x velocity may not be 0 on the outlet. So no slip is not required on the outlet because things can move out. So we will, but we are ensuring that the y velocity is 0. So things should not move out. There should not be any y velocity in the outlet. Okay, so but these can be changed. I mean, depending on what sort of outlet boundary works for us. Then this is the volume fraction. Again, volume fraction, we only need to solve for one phase. So we solve for air phase and copy that to water. So in the volume fraction, we have initial condition. So we have a very small volume fraction to start with everywhere. So this is 10 to the minus 7 amount of air. So that means mostly it is water in the column. There's not much air, in fact, almost 0. But we still keep a number to prevent any division by 0 problems. Then Sparger, that's the inlet. We have a flux boundary where the flux of air volume fraction is 0.06. So again, it's much comfortable to specify flux rather than specifying the actual volume fraction, because you will always have some amount of some kg per meter cube or some volume flow rate that you will specify. On the sides, we have a 0 flux, so nothing is moving from the sides or from the walls to the left and right of the sparger. For the outlet, we are not specified anything, so that becomes a natural boundary condition. That is a Neumann boundary condition. Right, so this is pretty much it. Now let's go to population balance. So population balance, this time we again have two weights and two abscissas. We solve for weights and weighted abscissa. And then for the source terms, we have aggregation and we have breakage. Aggregation, we are using now kernels which are more realistic because this is a physical problem. So this was given by Lakonen in their paper. Similarly, for breakage, we have the breakage frequency given by them. And we also have a dotted distribution function that was provided by them. So these are hard coded into the code, but you can go to the files. So in case you would want to see, I mean, we have not specified anything here. So you can always go to the code. So it says population balance. So here we have, so it's a Fortran based code. So you can go to this code, and then I'm searching for these kernels. So this is where we specify the different kernels. So if have breakage, if the breakage is there, then if breakage frequency is of type Lacanian frequency, then density continuous is this, density dispersed is this, sigma is equal to this, that's surface tension, epsilon NGI. So this is your epsilon, that is turbulent dissipation rate. So that is taken from the dissipation calculated in the K epsilon equation, and then we calculate the breakage frequency as this formula. So that's the good thing about having an open source code. You know what you're doing. With commercial software, you can only guess. You always may be confused whether it's correctly implemented, whether what I'm guessing is correct or not. So for researchers, it makes sense to have full control over what you're doing. For industry, where you want to get something out of it so that you can move forward and start with the design and so on. So there it makes sense to have something which is more user friendly, so that you don't have to spend a lot of time on learning all these things and then getting something useful out of it. So I always suggest that we understand how things work on the code level as well. All right, so that's it. Nothing else. Now you simply have to run it and then wait for the results. Now I have two different versions of, so I have a newer version of Fluidity. I am not sure whether this thing will even run, but let's try to correct these things first. So it needs a particle diameter. Now this particle diameter can be a constant or can be a scalar field. So now since I am solving for the population balance, then I can use some property out of it. So I have a Sauter mean diameter. Okay, that is nothing but it's a ratio of the third moment to the second moment. So this name is Sauter mean dia with S, M, and D capital. So all I'll do is I will say the particle diameter is a scalar field, and the name is Sauter mean dia. Save it. Similarly, when we calculate the particle Reynolds number, that requires particle diameter, that again can be a scalar field. So now nothing is blue, so that means all the errors are sorted. Not very helpful. So I'd got two versions of the files. Let's try this one. This might not work because it will need to initialize things using some other. We'll have to initialize things to 0 because this is a checkpoint. So checkpoint initializes fields from VTU. So this will not work. Let's try this again. So this is not working. So I probably got a wrong version of the FLML file. So you'll have to do a detailed study as to what is happening because this code has evolved since then, and we had modified this FLML file. But actually, we can look at the error file and see if this is not a very helpful error. And then let's look at the log file. Let's go to the end. So it started with the first time step, and then something to do with k epsilon, and then it had problem. So we'll have to figure out what exactly is happening here before we can continue further. Not sure if I have any other version of the file. Let's see. No. Well, that's not a problem. So I can share the latest working version with you later. So I now let's go to ANSYS. Does anyone have anything on Fluent to ask? On Fluent.
Yes.
Yeah, I wanted to say fluidity. Does anyone have a question about fluidity before we move to Fluent? Okay. So now let's go to Fluent and then we'll ask you for questions. So let's close this. So we will work with the 2D version and then let's keep it double precision, a serial processor for now. Let me see again. I have an old case file. Hopefully that opens here. So we have some sort of a geometry here. It's a square geometry. I don't really remember what exactly this file was, but we can have a quick look at it. So it's a pressure-based solver. It's a transient solver here. So the models we have is a multi-phase mixture model. That is not what I want to open. So let's look for something else. Yeah. So this looks more like a bubble column. So we have an inlet here, and then we have an outlet. So we have a multi-phase Eulerian model. In this case, we are using two Eulerian phases. Energy is off. Then in the Eulerian, we have water and air as two phases. There's a phase interaction between them, which is Schiller-Neumann drag model, the same that we were using in fluidity as well. And then it's a laminar case, so K epsilon is not enabled, and we can see that we have a population balance model enabled here. Actually, it is off right now. So we have different options available here. Okay, the one we want to go for is DQMOM, and then in this we can have parameters like minimum size and maximum size. So here they assume that this is the internal parameter here is its size. Okay? Particle size or the bubble size is the internal coordinate here. So we have an option for minimum size and maximum size, and we can have that's pretty much it. Yeah, so this is the phenomena. So we can have growth, we can have aggregation. So let's say aggregation. Aggregation has different models available. So if you want to use a turbulent model, then you'll have to go to the ANSYS Fluent theory guide where they tell you about all these models, and then you can have breakage frequency and the dotted distribution function, which again has different. So Laconen is available here. And here we have these four models available. You can also have a user-defined model where some user-defined function will have to be defined. So that is also possible. So and then growth rate can be enabled. Again, this was also available in fluidity. I didn't discuss that, but growth is also available there. So again, you can have a constant growth rate, or you can have a user-defined function here. Okay, so these are the source terms in the population balance equation, and then you specify these max and min sizes just to be sure that it does not go beyond or below these sizes. This is it will clip, I think, the sizes so that it never goes above or below those sizes. Then you can also have a quadrature method of moments here, which is a little different from DQMOM. So in quadrature method of moments that I discussed, that you track the evolution of the moments rather than the evolution of the weights and abscissas. So here you can specify how many moments you need. So first 4 moments, first 6 moments, and first 8 moments. These are the options available. And then you have a KV, a factor that relates the moments with the volume. And then you have a minimum and maximum size, so that due to some numerical issue, it does not go beyond or below a certain value. Because having extremely small particles will maybe unphysical, and having extremely large particles, more than 1 meter, will also be unphysical. Okay, so these are numerical checks rather than actually physics here. And you can have aggregation and breakage kernels as you had last time as well. That's pretty much it. Then you have to, let's actually do something here. Let's have 4 moments and some aggregation and breakage kernel. So this is enabled now. And then we can specify the initial conditions. boundary conditions here. So let's say on the wall, let's say we have a mass flow rate. I'm trying to see if we can specify some population balance relevant. Yeah. So since we enabled the population balance model, so now if I go to the air phase, it says in multi-phase I have moments available here from 0 to 3 because I enabled 4 moments. So I can now specify the boundary condition type. So a value Dirichlet or Neumann. So I can specify if it's Dirichlet, I specify the value. If it's Neumann, I specify the value of the derivative. So that ways I can specify the values or the fluxes, and that is how we specify the boundary conditions for the moments. Clear? Now the question that you might have is, how do I specify boundary conditions? I mean, let's think of these bubble problems where you have from the inlet, you have bubbles, constant size entering. So how will we specify the volume? I mean, what will the moments be in that case? So we know the number density function, which is in this case uniform because all the particles, which is peak at one point because it's only for one particular radius, one particular size that you have a non-zero number, otherwise it's zero. You can calculate the moments corresponding to that. You know a number density function, you can calculate a moment. That's using the formula of moments. And if you have a particle size distribution, a bubble size distribution, so if you're doing an experiment and you measure that sparging device that you have generates a certain distribution of bubble sizes. So from that distribution that you have, from the histogram that you have, you can calculate moments. Because moments, again, you can use the definition of moments. And then once you calculate the moments, you can specify them here, and that becomes your boundary condition. Okay. Again, we don't have any numbers here, so we can't run it. But if you have used Fluent, you know it's as easy as pressing the calculate button and then it runs. It actually runs with 0 moments as well. So we specified 0 moments there. Is that clear? Time is it? Yeah, almost 1 hour. So this was a very brief workshop / webinar where I've talked to you about fluidity and Fluent for running population balance modeling problems. So those test cases that are available in fluidity tests, you can run them and see what's happening there. And when you have to solve a real problem, then this bubble column problem is something that we can start with. Then we can modify it depending on how our domain looks, how the problem is. Any questions?